there is one question here. Now, that formula, what I told you, na, the del E is equal to 2.18 into 10 to the power minus 18. Supposing we are doing it for helium plus. Okay, there are some more questions of that type. So, supposing you are doing it for helium plus, then atomic number of helium is 2. So, we will take it as 2.18 into 10 to the power minus 18. 1 by, I'm trying to remove the electron, He plus. There must be 2 electrons. 1 electron is already gone. So, it's a single electron system and I'm trying to convert it into He2 plus 1 electron. So, I'm removing 1 electron. Where was it? It was in the first shell. Where is it going? It is going to the infinite shell into Z square. Is it clear? Huh.
Yes, ma'am.
Okay. So if you are talking about the ionization energy, that means you are removing the electron from the given principal quantum number and you are taking it to infinite shell. So this formula, which was the Bohr's equation, could be applied for hydrogen or hydrogen-like atoms. That's it. Only for these 3 cases. Clear?
Yes, ma'am.
Don't
Yes,
apply
ma'am.
for any others. The example for that I will tell you. See, 2.10. Look at this. Can I apply this equation? The same Bohr's equation to calculate. Electromagnetic radiation of the wavelength 242 nanometers is just sufficient to ionize sodium atom. Calculate the ionization energy. So can I apply the Bohr's equation for this case? Is sodium hydrogen or hydrogen-like atom? Come on, children.
No, ma'am.
Sodium is a multi-electron system, whereas hydrogen had 1 electron, He plus had 1 electron, Li plus 2 also had got 1 electron. Okay. This is not even applicable to beryllium. Beryllium 3 plus. It is not even applicable to that. So how it will be applicable to sodium? It's a multi-electron system where there are totally 11 electrons. So you cannot use the same equation even though the concept is same. Looks like that, no? Calculate the ionization energy. Correct? So what you will do? Simply E is equal to Hc by lambda. We cannot use the Bohr's equation in the case of sodium. Got it?
Yes, ma'am.
Yes, ma'am.
So here it is 6.626 into 10 to the power minus 34 times 3 into 10 to the power 8 divided by 242 times 10 to the power minus 9 joules per atom. Per atom, very important. One photon having so much of energy will only knock out 1 electron from 1 atom. So it is joule per atom. It is joule per atom. Got it? When photon of energy E equal to h nu or hc by lambda strikes the sodium, 1 electron is removed. So 1 photon knocks away 1 electron. So it is energy per atom. Clear?
Yes, ma'am.
Yes, ma'am.
Now, what is the question? Read the question. If I solve this, is this my answer? Check.
I'm
Do I
yet
have
to
to do anything? Convert it to
kilojoules per meter.
kilojoules. 1. Okay. Any other thing to be done? Look at this. Joule per atom, kilojoule per mole. What else? I'll divide this by 1000. That will make it into kilojoules. Anything else? Still it is kilojoule per atom. No. How to make it kilojoule per mole? 1 mole has how many atoms?
Ma'am, we should multiply it by our getting.
Yeah, you have to multiply it by Avogadro. Got it? This
Yes,
is for
ma'am.
one atom. For one atom, so much. Whatever you calculate, that much. So for 1 mole will have Avogadro atoms.
Avogadro number of atoms.
So
Yeah.
you multiply this quantity, what you got, into Avogadro number. Clear?
Yes, ma'am.
Okay.
Yes, ma'am.
Right. Okay. Whatever is left out, we will try to finish, then we will proceed further. Okay. Whatever is left out. Did we do this 2.11, children? 25-watt bulb emits monochromatic yellow light. Did we do that? Did we do that? No, na?
I'm about to try.
Sorry? Couldn't understand you, Kanika.
Oh, when you told you can try it from like you got to try till 2.12.
Okay. So 2.11. It says 25 watt. What is that? 25 joule per second. Watt is the energy. So much energy per second. So 25 joule is emitted by the monochromatic yellow light per second. Understood? A bulb is emitting 25 watt. A 25 watt bulb. That means it is emitting 25 joules of energy per second.
Yes,
Is
ma'am.
it clear? So that's its power. So what will we do with this? A 25-watt bulb emits monochrome. Monochrome. Have you ever heard in the cars and all when they say they will speak monochrome? It is in monochrome. What do you mean by monochrome?
Ma'am, black and white.
No, it is single color. Monochrome design. If you say the whole dress is pink from top to bottom, you say it is monochrome. Fine?
Yes, ma'am.
Cars, single tone, no other color. Inside, outside, everything is same. Then they say monochrome has been used, one color. So here monochrome refers to one wavelength. Okay, one color, that means one wavelength. Fine. So a 25-watt bulb emits monochromatic yellow light of wavelength. So wavelength is given, which is 0.57 micrometer, which is 0.57 times 10 to the power minus, what is micro? 10 to the power minus 6 meters. Okay, micro is 10 to the power minus 6. So 0.57 into 10 to the power minus 6 meters. Calculate the rate of emission of quanta per second. Rate of emission of quanta per second. A bulb is monochromatic and it is sending light. How much energy is it sending? It is 25 joule per second. If the wavelength of the photon emitted is so much, if the wavelength of the photon emitted is so much, then they are saying what is the rate of emission? That means how many quanta are sent out per second. So that means this bulb is sending a lot of quantas, na? So they are asking how many quantas per second. So what you will do? We will take E is equal to NH nu. See, there was a statement in the text that whenever atoms or molecules take in or give out energy, it gives it in the form of multiples of the photon. Remember? Am I audible?
Yes, ma'am.
Yeah.
Yes, ma'am.
So
Yes,
it is
ma'am.
actually sending it in the form of, it is absorbing or emitting. See there. He gave the name quantum to the smallest quantity of energy that can be emitted. Okay, and further he suggested that atoms and molecules could emit or absorb energy only in discrete quantities and not in continuous manner. Absorb energy only in discrete quantities. That means that discrete quantity is h nu. So energy of a photon can be higher if the frequency of the electromagnetic radiation is higher, or you can have more number of photons. You can have more number of photons. Okay. So NH nu. It would be NH nu. Hmm. So either I have two choices, right? If I want, I can take photon of low frequency, so low energy, or I can take photon of high frequency, so high energy, or I can keep the frequency same and take more number of such photons. Are we clear? Or I
Yes, ma'am.
take more
Yes.
number of photons of higher frequency. Is it okay? So all this speaks about the quanta. So now they are talking about that only. So what are they saying? Can we put it as energy total is equal to n times hc by lambda? Hc by lambda is the energy of a single photon. Energy of a photon. So if total energy is larger than the energy of the photon, that means many photons have been taken in, and that is what they are asking. Quanta per second. How many quanta per second? So what you will do, what is the total energy emitted? It is 25 joule is emitted per second. E total is 25 is equal to n times h. 6.626 into 10 to the power minus 34 into the 3 into 10 to the power 8 divided by lambda. Lambda is 0.57 into 10 to the power minus 6 meters. So is this not energy of one photon? If you divide the total energy by energy of one photon, will you not get the number of photons, children?
Yes, ma'am.
Yes, ma'am.
Radhika, is it clear?
Yes, ma'am.
Okay, yeah. Something similar is there again. I'll just track any other question is there. These are regular question. Calculate the wavelength, frequency, and wave number of light whose period is. What is period? What is period? Period is if you talk about time period or period simply, its unit should be seconds. Time period should be seconds. That means, doesn't it look like inverse of frequency? Frequency is per second. So can we say inverse would be in second? So time period is equal to inverse of frequency expressed in seconds. Clear?
Yes, ma'am.
Okay. So how to do question number 2.7? They have given you the period. That means they have given you the inverse of frequency to be 2 into 10 to the power minus 10 seconds. What is time period basically? The definition is the time required for one full wave to cross a point. The time required for one full wave to cross a point. The time required for one full wave to cross the point, to cross a particular point is 2 into 10 to the power minus 10 seconds. So if you know 1 by frequency is equal to so much, can you not find out lambda? Can you not find out wave number? We know C is equal to nu lambda. So if nu is known, C is a constant, can we not find out lambda?
Yes, ma'am.
And
Yes, ma'am.
what is wave number? Wave number is inverse of lambda. So first find out wavelength and then do inverse of it to get the wave number. Okay. 2.8, isn't it same, almost same as 2.11, children? Check. Isn't it almost same? Check. What is the number of photons of light with wavelength 4000 picometer that provides 1 joule? What do you have to do? Can we say this is the E total is equal to NHC by lambda?
Yes, ma'am.
Hmm? So E total is 4000 picometers. So sorry, 1 joule. 1 joule. N times 6.626 into 10 to the power minus 34 into again 3 into 10 to the power 8. You can multiply this and keep it. That will save your time, remember. Divided by 4000 picometers. So into 10 to the power minus 12 meters. Do all your calculation in SI units. Hmm? See, Shri here, if you want N, you should definitely know what is inverse of 6.626 into 10 to the power minus 34. times 3 into 10 to the power 8.
Yes, ma'am.
Why not keep it ready?
Yes, ma'am. I'll do that.
What is inverse of the product of these two? That will save a lot of time in such questions. Clear?
Yes,
But
ma'am.
it will add to the memorization. Either you spend time this way or you spend time during the exam to do the calculations. It's up to you. Whichever is easier
I'll
for you.
memorize it now. It's easier.
Either way, some people are, I'm not very good at memorization. I go by understanding. So I can't do that. So it depends your ability. Okay.
Yes, ma'am.
Okay.
Practice more.
So 14 done, 15 done, 16, 17, 18 and 19 we did. We have not done 20, 21 and all. Okay. So we have few more questions, I believe. Idella we did, no? 30th and all we did. Based on the quantum
Yes,
numbers.
Yes, ma'am. I did
Hmm.
that.
Now look at these. These are also 33 and 34 are also related to Bohr's model. Same, na? What transit? Did we do this question, ma? 33rd?
No.
See, this question 33. Question number 33. Okay, what transition in hydrogen atom, in hydrogen spectrum, should have the same wavelength? Okay, should have the same wavelength as the Balmer transition from fourth to second shell in helium. So there are two atoms under consideration. One is the helium, the other one is the hydrogen. In helium, what happens? Let me find the expression for lambda. It is 1 by lambda is equal to 1.09677 into 10 to the power 7, 1 by, isn't it now the 2 square minus 4 square, children? Meter inverse. Okay. Did I leave anything? I have left something. I forgot to introduce the Z value. What is the Z for it? 2. So we'll put it as 2 square. Correct?
Yes.
Okay. Now, what transition in the hydrogen spectrum would have the same wavelength as? So here also we will write the expression 1 by lambda is equal to 1.09677 into 10 to the power 7, 1 by n1 square minus 1 by n2 square times 1 square, meter inverse. So now they are saying that there is some transition in hydrogen whose wavelength value is same as the transition in helium if the transition is from 4 to 2. That means, can we imagine that this 1 by lambda of hydrogen is equal to 1 by lambda of helium?
Yes, ma'am.
Yes, ma'am.
In that case, then right side can be equated. If the left hand side, same wavelength for some transition in hydrogen corresponds to transition from 4 to 2 in helium. So if the left hand side are equal, right side can also be equated. So let me equate 1.09677. When I equate, obviously these two will get cancelled, right? That's same thing. So I'll put it as
Yes.
1 by n1 square minus 1 by n2 square into 1 square meter inverse is equal to 1 by 2 square minus 1 by 4 square times 2 square meter inverse, or we'll put it as 4. So what should be the value of n1 and n2 to make left hand side equal to right hand side? Can you guess? Can you
Ma'am,
take
1
this
and 2?
4? 1 and 2, yes. Can you take this 4 inside?
Yes,
Multiply
ma'am.
the 4. So this will become 4 by 2 square. This will become 4 by 4 square. 4 by 2 square will be 1 by 1.
1.
1 by 1 square. And 4 by 4 square will be 1 by 4. Which can be written as 1 by 2 square. No? If I take the 4 inside, I rearrange. So what looks like the value of n1 and n2? Can we say n1 is equal to 1 and n2 is
1.
equal to 2?
Yes, ma'am.
Yes,
Yes.
ma'am.
Okay. So the transition of electron from second to first in hydrogen will have the same electromagnetic radiation given out, same as when the electron moves from fourth to second shell in helium. Got it? In hydrogen atom, when an electron returns from second to the first shell, it gives out electromagnetic radiation, the wavelength of which is same as the electromagnetic radiation given when an electron returns from 4 to 2 in helium. Got the concept?
Yes, ma'am.
Yes,
Okay.
ma'am.
34th is simple. 34th just now we did. Try 34th. Calculate the energy required for the process. Is it not ionization?
Yes, ma'am.
He2 plus 1 electron. And they are giving you some reference value. Why they are giving you? The ionization energy, the del E, to remove electron from first to infinity in hydrogen atom is given as 2.18 into 10 to the power minus 18. So if you are talking about any other atom, how will you introduce? What will you modify it as? You should modify it as Z square. Correct? There was Z square. Since it was hydrogen, we took it as 1 square. It
Yes,
was
ma'am.
moving from 1 to infinity square. So 1 by infinity is anyway 0. 1 by 1 square is anyway 1. So if hydrogen's value is given, then calculate for this. What will you do? You just have to take the del E for helium from 1 to infinity. And what will you do? 2.18 into 10 to the power minus 80. Multiply it by the atomic number of helium, which is
2.
2 square. 2 square.
Yes, ma'am. 2
Atomic
squares.
number square. Is that okay? Comfortable with these questions?
Yes,
See,
ma'am.
the concept, when I
Yes,
did the
ma'am.
concept, it might have sounded very complicated, right?
A little more.
But now the questions are easy, na? Look at question
Yes,
number
ma'am.
32 and I'll tell you what it is connected with also. Read the question. Question number 32. Show that the circumference of Bohr orbit for hydrogen atom is an integral multiple of the de Broglie wave. Oh, we didn't do de Broglie wavelength, so we'll stop. Not. Okay, I think the rest of all these are like your maths now. Okay, see these I am not going to do. These we'll call it as miscellaneous. Look at the question. Do you need any guidance in these questions? See, look at these two. Any guidance is required?
No, ma'am.
The diameter of a zinc atom is so much. Calculate the radius of the zinc atom in picometers and number of atoms present in a length of 1.6 centimeter if the zinc atoms are arranged side by side. Any problem in that? The diagram of one atom is 2.6 angstrom. 2.6 into 10 to the power minus 10. Now they are saying that you have got a 1.6 centimeter line. So how many atoms of zinc should be placed side by side? Easy, na? 1.6 divided by the diameter of a single atom will tell you, right?
Yes, ma'am.
Yes, ma'am.
Okay. 38th. A certain particle carries 2.5 into 10 to the power minus 16 coulombs. 2.5 into 10 to the power minus 16 coulombs of static electric charge. Calculate the number of electrons present in it. What do you have to do? Calculate the number of electrons in it. This is the total charge. What do you have to do? What to do?
The
This is
total charge by the
ah,
charge of one electron.
That's all. Total charge by charge on one electron. 1.6 into 10 to the power minus 19 coulomb will give you the number of electrons. Is it okay?
Yes, ma'am.
These are all that you can do. This is purely maths. Symbol of, okay, this is at least something. But next you see, an element with mass number 81 contains 31.7% more neutrons as compared to protons. Assign the atomic symbol. An element with mass number 81. So mass number is 81. That means, isn't it protons plus neutrons? An element with mass
Yes.
number 81 has 31.7% more neutrons as compared to that of protons. If the protons are P, what are neutrons then? Isn't it P plus, what will you write? Come
P
on.
plus
Hmm.
by 100.
Into P, right?
Yes, ma'am.
This will be the number of
31.7
neutrons. Yeah.
by 100 into P.
Understood?
Yes, ma'am.
Further, what are
Yes,
they
ma'am.
saying? Assign the atomic symbol. So from this data, you can calculate what? You have a single variable, which is P, right? So if you know the protons, that becomes the atomic number. With the help of atomic number, you can write the symbol. You can identify the atom by looking at the number of protons only, no?
Yes, ma'am.
Okay.
Yes,
See,
ma'am.
other questions are also quite simple. Like this is about 1 unit negative charge. So there will be one extra electron. Okay. It has got 11.1% more neutrons than the electrons. Remember, when there is a unit negative charge, there is one extra electron than the number of protons. So you can make a mathematical equation and generate this. All these are same. Can you do this 2.46? Check. Nitrogen laser produces radiation of this wavelength. What do you have to do? 2.46.
We have to find the total energy by the number of photons is equal to total energy by
So,
the energy of one photon.
okay. If the number of photons is it by, or is it n is given in hc by lambda, na? So you are given these two quantities, na? Number of photons is given and you are given the lambda. So energy of one photon into number of photons per second. Will it not become the power?
Yes, ma'am.
Okay. So these questions I am leaving it to you. This also I'm leaving it to you. Please do it and tell me in the next class. Okay. The longest. Okay, we can do now after we have done. I'm giving up to 49. Question number. You can start from 37. Even this. See 35 to 49. Okay. 35 to 49. Clear? Do it as homework and see if you have any difficulty, we will discuss.
Yes, ma'am.
Okay, so I'm going back to the concepts now. Now, Bohr's model is what were the postulates of Bohr's model? We'll go back to that. Okay, Bohr, using the spectral study, gave some conclusions. Okay, gave some conclusions. So, spectrum and the Bohr's model happened actually side by side. So, Bohr's model for hydrogen atom was based upon the Planck's concept of quantization of the energy, and also based on the atomic spectra of the hydrogen atom. So Bohr's model for hydrogen atom, because the spectrum was studied only for hydrogen. For others, if I study the spectrum of helium, Okay, I think I was mentioning this, that helium is a 2 proton, 2 electron and 2 neutron system, correct? Okay,
Yes.
compared to hydrogen. Hydrogen is 1 proton, 1 electron. So there will be only attractive force between proton and electron. But here, there will be attractive force between proton 1 to electron 1 and electron 2. Proton 2 will attract electron 1 and electron 2. So these many. Then proton and proton will repel because they are like charges. Electron and electron will repel like charges. So there are many forces due to which the spectrum looks complicated, and you cannot interpret the spectrum of anything other than a single electron system. Clear?
Yes, ma'am.
But
Yes.
but it becomes like a fingerprinting. Okay, I think that I discussed last class itself. So we'll go back to the postulates. So this is the usual number, whatever we have understood so far, that the Bohr's model suggests that the electron in hydrogen atom can move around the nucleus in circular path of fixed radius and energy. These paths are called as orbits, or they are called as stationary states or allowed energy states. That means an electron in hydrogen can be residing in n is equal to 1. If not there, it can be in n is equal to 2. If not there, n is equal to 3, and so on. But that means when the moment you know the n value, that it is n is equal to 1, its energy gets fixed. The energy of an electron gets fixed. So either the electron will have even amount of energy, which is minus 2.18 into 10 to the power minus 18 by 1 square, or it should have minus 2.18 into 10 to the power minus 18 by 2 square. Either an electron has even amount of energy, or next to that E2, next to that E3, and so on. So electron can possess only certain allowed energy values. In between E1 and E2, there are infinite values, but none of them are allowed in atoms. Is it clear?
Yes, ma'am.
Yes.
Okay. Then the energy of an electron in an orbit does not change with time. Okay, this explains the stability, because in Rutherford's model, around the nucleus, the electron was not having fixed energy. So being charged in nature, getting accelerated in order to maintain the circular path at one point of time, it should have hit the nucleus. According to Rutherford's model, that is, Rutherford did not suggest that atom will explode. But the people who were analyzing the Rutherford's model suggested that if your model is accepted, that means all atoms should undergo dissociation. Bombardment, nothing happens. So your model is faulty. So that this was a correction. Bohr provided a correction. He said that as long as an electron is present in a given orbit. Okay, the word orbit was given even by Rutherford, that electrons are revolving in orbits. But he did not talk about the stationary energy. He did not define the energy. So other people who were interpreting would say that the electron would move closer to the nucleus and hit. Contrary to that, Bohr discussed that the electron's energy, as long as it is in a given principal quantum number, remains fixed. It remains fixed. 1 minute. Remains fixed. But however, if some energy is given equal to E2 minus E1, then the electron would like to shift into the second shell. Right? Or if it is given E3 minus E1, it can go to third shell. So, however, the electron will move from lower stationary state to higher stationary state when required amount of energy is absorbed by the electron, or energy is emitted when electron moves from higher stationary state to lower stationary state. The energy change does not take place in continuous manner, but it takes place in discrete manner, in quantized manner. Got it? If I'm repeating this, please let me know. Okay. Did we discuss these two? Angular momentum? Yes, I think. No? I did discuss, right? I did, na?
Yes, ma'am. Yes, ma'am.
Okay. And what about the Bohr's radius? That also I discussed. The Bohr's radius is 52.9 picometer. The radius of an electron located in the nth shell will be a n square. This also we discussed, right? Okay, just to summarize, if I know the electron is located in the nth shell, then I can calculate its energy, the electron's energy from minus 2.18 into 10 to the power minus 18 z square by n square. I can calculate the angular momentum with it, which is n times h upon 2 pi. So supposing the electron is belonging to the second shell, then what is the angular momentum? It will be 2 times h upon 2 pi. Clear?
Yes, ma'am.
It
So
cannot
that's
be 2.5 times h upon 2 pi. That means an electron can belong to either one, first shell, or second, or third, or fourth, or fifth. Any integral number is okay, but not fractional value. So it also points to the fact that the electrons are present in quantized energy levels. Only certain allowed energy values, only certain allowed angular momentum values, only certain allowed radius values, which is a n square, which is 52.9 into n square picometers. So once you know the electron's principal quantum number, you can identify its energy, its angular momentum, and radius. Is it okay? So if you substitute n is equal to 1, you get some values of the three quantities. If it is n is equal to 2, a different set of values. That means in between the two, there are infinite values. Those are not allowed. Are we clear?
yes, ma'am.
Okay,
Yes, ma'am.
right. Okay. Then, now, okay, this is the explanation for the line spectrum of hydrogen. So we arrived at the Balmer's equation. Remember? Balmer's equation. Okay, and they are
Yes,
interconvertible
ma'am.
and indicating that both refer to the same concept. What you can do is, I was telling you del E is equal to 2.18 into 10 to the, I think I did tell you about this, 1 by n1 square minus 1 by n2 square into z square. If you take the mu bar, which is equal to 1.09677 into 10 to the power 7, 1 by n1 square minus 1 by n2 square into z square, then if you multiply this del E, okay, is nothing. We know E is equal to hc by lambda. Wave number is 1 by lambda. Okay, so if I multiply here hc, see, if I multiply hc and hc, can I call this quantity as del E?
Yes, ma'am.
And this quantity will now become what? 2.18 into 10 to the power minus 18, indicating that the Balmer's equation and the Bohr's equation are one and the same.
Right, yes, ma'am.
Okay.
Yes, ma'am.
Similarly, you can rearrange this and say E by hc is equal to 1 by lambda. So if you divide both of them by hc, this quantity will become what?
1 point.
This much. Indicating that both the equation refer to the same concept. They point to the
Yes,
same
ma'am.
factor on the atom. Okay, now, so that concludes our Bohr's model. Now, what is the limit? Is the Bohr's model the most accepted model till today? No. We have learnt about the quantum numbers. Remember that the
Yes, ma'am.
electronic configuration is described in terms of 4 quantum numbers, namely principal quantum number, azimuthal, magnetic, and spin quantum number. That was as per quantum mechanical model. So there must be some problem with the Bohr's model. Okay, there are
Yes, ma'am.
some limitations to the Bohr's model. So what were the limitations? See, so far picture was okay, understandable. But supposing, again, coming back, a sample of hydrogen atoms was irradiated with continuous spectrum Some part of it was given out, which formed absorption spectrum, and some part of it hydrogen used for causing the transition. And as the electrons returned, those were given out and they were forming the emission spectrum. And both emission and absorption spectrum are line spectrum. That means they are not continuous, correct?
Yes, ma'am.
Okay. Now,
Yes, ma'am.
if you place electric field in the path of the spectral study, during the spectral study, I'm going to put an electric field, strong electric field. Okay, that means this is one plate, this is another plate, and I provide it with a large amount of charge, say 20,000, 40,000 volts current. What will happen? In between the two metal plates, we will say that the electric field is generated. So the whole spectral study is now in the presence of electric field, correct?
Yes,
Yes, ma'am.
Okay. Now what happens is, now after introducing the electric field, they again got the emission spectrum. And surprisingly, they found that the emission spectrum has some additional lines. Some lines were missing, and in the place of those missing lines, some additional lines were established. So it looked like say, one particular line was missing, and it actually appeared as two distinct line in the spectrum. That means that line seemed to have broken into two parts, or we call it a splitting of the spectral line. Are you able to understand the concept? The emission spectrum would look like certain pattern. When the same study was performed in electric field, the pattern was slightly modified with most of it same, but probably one of the lines were missing, and instead you got some more lines here. So this looked like this line has got split into two, correct?
yes, ma'am.
Yes,
So
ma'am.
if hydrogen atom is well understandable, everything is fine so far, then on the basis of that model, they should have explained what is the reason that the splitting of the spectral line is taking place in electric field. If you know something so well, you should be able to predict the behavior. You should be able to explain the behavior. No?
Yes, ma'am.
But the splitting of the spectral line in the presence of electric field could not be explained. That means there is something wrong with the model of the atom as proposed by Bohr. Okay.
Yes, ma'am.
Similarly, when the process was repeated with magnetic field, that means a pair of magnets was placed and emission spectrum was observed. Again, they saw that the emission spectrum was getting modified. Okay, some lines were getting split. Okay, so Bohr's theory was not able to explain the splitting of the spectral lines in the presence of magnetic field, which is called as Zeeman effect. They will ask you, what is Zeeman effect? Okay, or Stark effect. What is Stark effect? The splitting up of the spectral lines in the electric field. So it fails. The Bohr's model fails to account for the finer details. Doublet. Doublet refers to two closely spaced lines. We will talk about one of the question here. You see one question. See 2.50. Want you to focus on that. It's not an explanation to that, but it is related to that concept. The longest wavelength doublet absorption transition. Are you able to understand this doublet? In the spectrum, sometimes there occurred doublets, two closely spaced lines of the hydrogen atom using sophisticated spectroscopic techniques. The Bohr's model was unable to explain these closely spaced lines. Okay.
Ma'am, so the previously it was one line alone, and now it's a
No,
doublet.
in the spectrum of any atom, would you get only one line, Shri? You are doing
No.
the spectrum analysis for a batch of hydrogen. In every hydrogen, it's wish because you are giving all sorts of food. So in one hydrogen, electron could have been sent to the 10th level. And when it returns, it will return in small energy packets. In
Yes,
another
ma'am.
hydrogen atom, it could have caused the excitation to 7th level. And when it returns again, it could have given out the energy in small packets. In another hydrogen, simply to the 2nd level. So it will not comprise of just one line. It will comprise of many lines,
Yes, ma'am.
Okay, but overall, we know that this is the emission spectrum. This is how it should look like. But when the same spectrum was studied in electric or magnetic field, probably this one line split into two lines. Rest
Yes,
of
ma'am.
the
That's
pattern
what I
remained the same.
was. Yes, ma'am. I
So
get that.
no emission spectrum will just be made up of one line. It will be having
Yes,
many
ma'am.
lines because many atoms are there, many choices are there. Okay. This model
Yes, ma'am.
also was unable to explain the spectrum of atoms other than the hydrogen. For example, helium atom which just possessed two electrons. It became very complicated. And I told you why it became complicated for helium. There are many forces to talk about. Electron repulsion, proton repulsion, two electrons attracting two protons attracting two electrons. All that became too complicated. So, though we could do the analysis and keep it as a reference picture, interpreting helium or lithium or sodium or potassium spectrum is next to impossible. We can have a picture of it. It will look like if you see a modern art. Okay, can you exactly replicate it?
No, ma'am.
No. Yeah, like that it would be. It would be too
Yes.
complicated, but you can recognize, yeah, this is what the spectrum of helium will look like. This is what the spectrum of lithium will look like. But you cannot interpret. You cannot interpret it, put it in mathematical format. You cannot propose
Yes,
mathematical
ma'am.
equation for the radiations on that. Okay, second major drawback was that so far that whatever we studied now in 11th standard, in 10th we know how is NaCl formed, how is CH4 formed, right? Ionic
Yes, ma'am.
bond, covalent bond. But so far in class 11, whatever we have spoken about in Bohr's model or Rutherford's model, does any one of them talk about the formation of a chemical bond?
No, ma'am.
So, according to Bohr's model, you cannot interpret what is a chemical bond. So, that became one of the most important failures. It could not explain the ability of atoms to form the chemical bonds. Understood?
Yes, ma'am.
Okay. In other words, taking into account the points mentioned above, one needs a better theory which can explain the salient features of the structure of complex atoms. Atom itself is very, very complex now because you are unable to explain why Zeeman or Stark effect would happen. You could not explain why the chemical bonds are formed. What is the need for forming a bond? What is a bond? According to Bohr's model, nothing is clear. So we need some more theories. And to understand those theories, and the theory that is currently in place is the quantum mechanical model. Actually, the quantum mechanical model is something which is normally done in postgraduate level. You are here to study its results. The results are the quantum numbers, which we have already studied. Got it? We have applied the
Yes,
results.
ma'am.
Okay. But we need to know what led to the quantum mechanical model. So what led to quantum mechanical model was two important developments which contributed significantly in the formulation of the quantum mechanical model was the dual behavior of matter and the Heisenberg uncertainty principle. It was much after Bohr's study that the dual behavior of matter came out. It's not very, around 100 years back. Okay, is it clear?
Yes, ma'am.
Okay. So again, it's very, very thought-worthy process that the human race is existing on the earth for many, many thousands of our culture is, they say, 5,000 years old. Okay. But people came to know to all these theories only in last 100, 200 years. You understand the scenario, children?
Yes, ma'am.
Okay.
Yes,
And from there, where we have taken now, there is now there is like a transmission of electricity without even requiring the poles, without even requiring the cables. So to that level we have come, right? So it must have been very rapid development in the last 100, 200 years. Okay, it was
Yes,
very,
ma'am.
very significant. Okay. Okay, now what is this dual behavior of matter? So you remember where we started with? We started with the dual behavior of light. Remember? We started with dual behavior of light. When was Bohr's model introduced? 1913. And when is the dual behavior of matter being proposed? 1924. Okay. Got it? Okay. So
Yes,
he
ma'am.
started with the using light to have particle and wave character. Similarly, the matter is supposed to be dual behavior of electromagnetic radiations. That led to, because earlier, okay, the particle nature of light posed a dilemma for the scientists. Okay, like no, people were the only way to resolve the dilemma was to accept the idea of the light possessing both particle and the wave-like properties. So it was not very like ancient that people talked about the dual behavior of electromagnetic radiation. Now we are forced to talk about the dual behavior of matter. Okay. So why the rules and regulations of an object is not actually uh, being followed by electron? Probably electron also has wave character. So what do you mean by dual behavior of matter? Okay. French physicist de Broglie in 1924 proposed that matter, like radiation, should also exhibit dual behavior, both particle and wave-like properties. Okay, this means that just as photon has momentum as well as wavelength, electrons should also have momentum as well as wavelength. Photon is what? Energy packet. Light is made up of energy packets called photons. So photons have got some mass. Okay. Okay. Like photons have momentum as well as wavelength. Okay. Similarly, an electron also should have both the wave-like behavior and particle-like behavior. So when you say wave-like behavior, then it should have some wavelength. The wavelength for the electron or a particle like electron was proposed to be equal to h upon mv. De Broglie proposed that the particles, the so-called objects, okay, be it large or small, should have both wave-like and particle-like nature. The wave-like nature means it should be in the form of a wave, it should be exhibiting a wave. And if it is exhibiting a wave character, then there should be wavelength. The wavelength associated with an electron is equal to h upon mv. It's not about just electron. It's about your book. It's about an elephant. It's about a train. It's about a dust particle. It's about a proton, neutron. So the wave-like character, the duality of matter, the dual character, that is matter consisting both wave and particle, is applicable to all macroscopic objects and microscopic objects like electron, dust particle, neutron, proton, etc. But it is more significant for microscopic objects and less significant for macroscopic objects like these. Is the concept clear? It was a proposal. Okay?
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
Am I there? Am I audible?
Yes, ma'am.
Yes, ma'am.
Am I audible, Ganika, Shri?
Ma'am,
Yes,
you
ma'am.
are.
I can't hear you. 1 minute. Maybe the earphone went off. 1 minute. Now I'm able to hear. Tell me. Is that fine?
Yes, ma'am.
Yes, ma'am.
So it was proposed by de Broglie that, like how electromagnetic radiation was thought to have the wave-like and particle-like behavior, even the matter also had the wave-like and particle-like behavior. Okay. And the wavelength associated was equal to h upon mv. Assuming that we have a cricket ball weighing, let us say, 200 grams. That means it is 200 into 10 to the power minus 3 kilograms. Let us substitute. What is the Planck's constant value, children?
6.626 into 10 to the power minus 34.
6.626 into 10 to the power minus 34 joules second by an object, the cricket ball, with 200 into 10 to the power minus 3 kilograms. Everything in SI units times. Assume that the ball is moving at a speed of, can we put it as 30 kilometer per hour? Okay. Fast bowlers, like many of them, will be able to throw it at even 100, 160 also. So we'll put the velocity at 100. 100 by 3600, correct? Oh, 100 kilometers. So 100 times 10 to the power 3 meters by 3600, correct? So I'll use this. Is that calculation okay? Conversion
Yes,
part
ma'am.
is fine. By this
Yes,
is
ma'am.
200 into 10 to the power minus 3 into 100 into 10 to the power 3. So this will anyway go off. These will go off. Okay. So what will be there? You will have something around 3.313 into 336. So even if you ignore all that, something like 36 into 3 times, which will be around, say, 110 times 10 to the power minus 34 meters. Do you think this wavelength value is good enough to be measured?
No, ma'am.
110 meters divided by, it's too small. I have to write 34 zeros. So many parts into which it is divided. So lambda is so small for the cricket ball that the wave character of the cricket ball becomes very negligible. Clear?
Yes, ma'am.
Whereas if I try to do the same calculation for an electron, let us do. Lambda is equal to 6.626 into 10 to the power minus 34 joules second by electron's mass, which is 9.1 into 10 to the power minus 31 kilograms. I doubt whether they will give you this. They may give you, they may not give you. You should know. The charge on electron is 1.6 into 10 to the power minus 19 coulomb. And the mass of it is 9.1 into 10 to the power minus 31 kilograms. You should know. If it is traveling at the same speed, 30 into, or 100 we said, 100 kilometers per hour. So what it will be now? Like, this will be 6.6 into 36 by 9.1 into 100. Okay, we'll cancel that. 100, 10 to the power 5, 10 to the power minus 26, 10 to the power minus 26. Going up, it is 10 to the power minus 34, 32, and you are bringing up what? 10 to the power 26. So what will this value be? This will be something into 10 to the power minus 6 meters. Is it not an appreciable wavelength
Yes, ma'am.
as
Yes,
compared
yes.
to the previous value, which was 110 into 10 to the power minus 34? So as soon as the particle size becomes so small like an electron or a milligram sized object or a microscopic object, the lambda value becomes so prominent that you cannot ignore the wave character. Okay, so the electron is having wave character is the conclusion. So why actually the Bohr's model failed? Because all this time up to this, Bohr treated electron to be only a particle.
Good.
It never treated it to be a wave.
Oh,
Yes.
So in quantum mechanical model, the electron is also treated as a wave. It's treated as a particle having some energy, but it is also treated as a wave. Are we clear?
yes, ma'am.
Yes,
Okay,
yes.
so we are stopping with this and we will go to the Heisenberg uncertainty principle in the next class. So go up to this and finish up to this. There are some numericals, but you do at least these problems. Okay, there are some numericals based on the de Broglie wavelength. Again, one more thing, a caution here. Okay, here also wavelength is there. Is this wavelength concept same as the wavelength 1 by lambda is equal to 1.09677? What was that lambda for? What is this lambda for? In the
This
Bohr's,
lambda was for light. This is for light.
this lambda is for an object behaving as a wave, whereas that lambda was when an electron is moving from one level to the other, electromagnetic radiations are given out. So that lambda was for the energy given out, whereas this lambda is about an object behaving as a wave. So never see formulas as formulas, children. They should be seen as a concept. Calculate the lambda. அப்படின்னா தெரிஞ்ச lambda equation எல்லாம் எடுத்து போட்டுறக்கூடாது. Understood?
Ma'am, on the last part, can you
No, I'm
don't
saying
get
we now have lambda is equal to h upon mv according to
Yes,
de
ma'am.
Broglie's equation. In the spectrum study, we saw it is 1.09677 into 10 to the power 7, 1 by n1 square minus 1 by n2 square. Now, if they ask you to calculate the wavelength in any context, will you go and randomly pick any equation? So what you will do, you will go and check what concept it is about. Is it about the wave nature of matter, or is it about the electromagnetic radiation given out by an electron during the transition? Correct?
Right, yes, ma'am.
Understood? அதே மாதிரி see இங்கேயும் ஒரு wave function, wavelength வரும். The work function of cesium, okay, was irradiated with the wavelength. So in many contexts you have, what is this? When photon of a suitable wavelength was irradiated on a metal, electron was ejected out. So every time you will go and check the concept, what concept it is. Then only you will go and pick the formula.
Okay, ma'am.
I
Yes,
hope both of you are clear with that.
ma'am. Yes, ma'am.
Yes.
Is it okay? Okay.
Yes,
So
ma'am.
I'll just spot one question related to this concept. Okay. See here. Question number 2.60. Check this also. The velocity of an electron in the Bohr orbit is 2.19 into 10 to the power 6 meter per second. Calculate its wavelength. Of course, they have said de Broglie. Even if they had not told that it is de Broglie, you should be in a position. The velocity of an electron in the Bohr's orbit. Calculate the wavelength associated. So electron is treated as an object which is revolving around the nucleus. Understood?
Yes, ma'am.
So you will go to de Broglie equation.
Yes, ma'am.
Okay, check this. The velocity associated with the proton moving in a potential difference of 1000 volts is so much. If the hockey ball of mass 0.1 kilogram is moving with this velocity, calculate the wavelength associated. So you have three equations. What are they? Hc by lambda is equal to hc by lambda naught plus half mv square. This is one, this is other, this is the third. Which one of the three will be applied here in this case? A hockey ball is moving.
The third.
This one, no?
H
Not
prime.
this, I believe. Kanika, this one only, no?
Yes, ma'am.
The H prime.
Understood?
Yes, ma'am.
Yes, ma'am.
Hmm. Okay, so go by the concepts, okay? So
Yes, ma'am.
that is why the concept is being told at length. Otherwise, we could have listed out the further. See, look at this 2.20. Calculate the wavelength of an electron moving with the velocity. Is it not de Broglie wavelength?
Yes, ma'am.
Electron is moving. But here, electron is only moving at a velocity. But here, is it not about transition? Calculate the wave number of the longest wavelength transition in the bulb. Is it not electron moving from one level to the other and returning? Understood
Yes,
which
ma'am.
concept to apply where?
Yes, ma'am.
Hmm?
Yes, ma'am.
Yes, ma'am.
Yeah, okay. Right. Okay. So we will stop the class. Next class, we will start with the Heisenberg uncertainty principle. After that, it is a very small content left out. Okay.
Okay. Yes.
Right. Okay. Right.
Thank you, ma'am.
Thank you, ma'am.
Yes.